Welcome back to separations. In a previous flash distillation example problem, the problem asked me to evaluate whether or not a certain composition was possible in one of the products. And I concluded that it was not possible because I ended up getting a negative flow rate, and therefore this would violate the material balance. So given this interesting result, a logical question to ask is, what would be the limits of a single stage distillation unit? And in order to answer this question, this is where having an understanding of how the graphical solution works is going to be really, really informative. So I'm just going to go back and review how you do the graphical solution for a flash distillation problem. The entire graphical solution occurs on a graph of Y, the vapor phase composition of component A, versus X, the liquid phase composition. And typically when we draw this graph, we have the Y equals X line that is drawn at a 45-degree angle where Y is equal to X. And the equilibrium data is set by the identities of the two components. Typically it'll look something like this. So you can get this equilibrium curve by plotting the alpha equation. So this is the equilibrium curve. You can also get it by Raoult's laws or by converting the TXY diagram. So typically Y is equal to alpha X over 1 plus alpha minus 1 times X. And the other part of solving an equation like this, or a problem like this, is knowing what the operating line is. So remember that the operating line has an equation that is derived from the material balance. Y is equal to minus L over V times X plus F over V times Z. At this point, I also want to highlight some alternative notation that you may see this equation written in. So we'll call this alternate forms of the operating line. And sometimes it's convenient to talk about percentage of feed that is vaporized or percentage of feed that remains liquid. So an example of that is sometimes the lowercase f is designated or assigned the value of V over F. And this is the fraction of feed vaporized. I don't know why they call it the letter F, maybe for fraction, but then there's another one that doesn't really make sense. Fraction of feed vaporized. And by using this definition of the variable combined with the overall material balance, you can obtain the following form of this equation. So say instead of knowing what L and V are, you knew what little f was, the fraction of feed vaporized, you could also write the equation like this. So you could also show this yourself with just a little bit of algebra. Negative 1 over f times x plus z over little f. This equation is exactly equivalent to the equation I derived last time. So the only difference is what is it in terms of. You notice this equation is a little bit simpler because I only have one parameter, little f. So if I know what V over F is, sometimes it could be simpler just to do this equation. Another way I could define it is with the lowercase letter q. And at the risk of being confusing, because q is going to stand for something else later, q in this case is going to stand for L over F, or fraction of feed that remains liquid. Remaining liquid. And if you use this as the form to convert, you are left with y is equal to minus q over 1 minus q times x plus brackets 1 over 1 minus q times z. So once again, any one of these three definitions for the operating line will work. They are all equivalent, and it just has to do with A, what you're given, and B, what's most convenient for you to plot. Now notice that the slope of this line is dependent on L and V in some way. So even though in the other two equations they're in terms of little f and little q, these are dependent on L and V as well. So what are the limits of L and V? Well, theoretically, either L or V could be 0, but none of them could be negative. So L and V are both somewhere between 0 and F. Right, I can't go higher than F, and same thing for V. 0 is less than V is less than F as well. Therefore, because L and V both have to be positive numbers, and I'm taking the negative of it, that means the slope of this operating line must be negative. So in other words, it must be sloping down as we go towards the right. So let's push it to the limits and see what happens. Let's first explore the case for L is equal to 0. So we'll call this limit 1. If L is equal to 0. Well, if L is equal to 0, then that means that V, being that it's F minus L, must be equal to F. So V is equal to F. What happens to the slope of the operating line in that case? So for L is equal to 0, we have Y is equal to minus 0 over F, X, which is 0, right? Don't be confused by this, plus F over 0 times Z. So that means that my intercept is going to be undefined because I'm dividing by 0, and also that my slope of this line is going to be negative. Oh, wait, no, I'm sorry. I plugged in the wrong number. V is equal to F. So F over F is equal to 1. So this means my slope is 0, meaning operating line is going to be a straight horizontal line. Operating line is straight horizontal. All right, so in my diagram up here, if this is my Z, remember that at X is equal to Y is equal to Z, that is a point that is on the operating line. If my operating line is horizontal, that means that the lowest possible YA that I can get and lowest possible XA that I can get is here. So this is XA minimum, and this is YA minimum. And this comes from if I vaporize 100% of the feed. Now you may be asking, you may have a question here, if I vaporize 100% of the feed, then am I actually performing a separation? Let's look and see what the process flow diagram would look like. So this is single stage, and I've got F, Z. We don't have to assign numbers to this yet. All right, but I've got V is equal to F and L is equal to 0. And I am saying that the compositions that you will see are going to be somewhat strange, right? So Y and X. But looking at the operating line, right, part of it makes sense, right? If I look at my Y coordinate, my Y is going to be equal to Z, right? So Z is here. ZA, because I know that that has to be on the operating line. I'm going to erase that one just for clarity right now. Right, so for a straight horizontal line, all of my Y coordinates are equal. So this means that YA is equal to Z. My X is equal to XA minimum. But how is that possible, right? If I'm vaporizing everything, shouldn't the compositions of all streams be the same? And because we're thinking about a limiting case here, we really don't want to evaporate everything. So the thought process goes like you're evaporating everything except for one tiny drop. And because it's such a negligible drop, we say it's close enough to be 0 anyway. So again, this is a limiting case, and that means that even though there is 0 liquid product coming out here, we still say that there's one little tiny droplet left. Just enough that we can measure what the composition is. One tiny droplet. All right, at the limit. At the limit, in order to still be at equilibrium, which is one of the stipulations of the single stage, remember, if we evaporated literally everything, then we wouldn't be at equilibrium anymore. We wouldn't actually have a single stage process. So all we're trying to do here is, again, try to map out what the limits are such that we know that our process is falling in between these limits. All right, so this gives us some ideas of what the minimum possible YA should be. Remember also that minimum possible YA is, minimum possible XA is corresponding to maximum possible XB. All right, so those two things go hand in hand. Okay, so that's the one limit. Let's go over to the other limit now, and now say that V is equal to 0. So limit 2, if V is equal to 0 now, then L must be equal to F, and we haven't done very much vaporizing anyway. So here, once again, we're going to say that we're not actually literally evaporating nothing. We are only evaporating enough such that a single bubble of vapor forms. So my V here is close enough to 0 such that it's not really measurable except for the composition is measurable. Well, instead of saying equal, we'll say approximately equal to 0. Right? So this means one tiny bubble of vapor is forming. And by looking at the, L is equal to F here. By looking at how the lines are drawn, that can inform us to what the composition of Y must be. So here, X is going to be equal to Z, and I have an F and a Z that remain. Y is going to be Y max. Let's look at what the equation for the operating line is. So Y is equal to minus L over V, so minus F over 0 times X plus F over V, and V is equal to 0, so F over 0 times Z. So here we've got two things that are both undefined. So this is undefined, and this is also undefined. This means that our operating line is a straight vertical line. Is straight vertical. Right, so up here on my diagram, I'm going to just use the same diagram here. Maybe I'll use a different color so we don't confuse. The straight vertical line starting at ZA would look like this, and this would be my YA max. And the corresponding point at ZA would be my XA max. All right, so this type of analysis allows me to say that no matter what fraction of the feed that I evaporate or what fraction I remain as a liquid, I know that my compositions have to lie somewhere within here, which reflects the fact that both of my flow rates have to be positive and less than F, such that the slope, this minus L over V, is a negative number. Right, so whatever my operating line is, I can draw in whatever I want, or I can design the process to be however I want. But that is the one thing that must be true, is that I must have a negative slope, and it is bounded by the gold line and the blue line, which in turn inform me as to what my compositions are possible. That is all for this video. See you in the next video.